Hi there, my name is Ben Rodney with ASHRAE New York, and on behalf of the ASHRAE New York Board of Governors, I want to welcome you to this recording of our guest speaker at this monthly chapter meeting. We're excited to continue to bring content to our members and guests and hope that you'll follow our new YouTube channel by hitting the subscribe button just below this video and then hitting the bell to get notifications on any content posted to the channel. You can also follow us on LinkedIn, Instagram, and go to our website, ASHRAENY.org, where you can sign up for our newsletter, check our events calendar, and hopefully join us as a new member of the chapter. If you have any questions, comments, or conversation about this video, just leave them in the comments section below. Thank you, and enjoy the presentation.
Welcome to the April dinner meeting. Very excited to have everyone here. We hope everyone is doing well. So a few, as usual, housekeeping items before we begin. One would be, please make sure that upon leaving the webinar that you fill out the survey. This is how we are doing attendance for PDH credits. So we want to make sure that everybody receives it that needs it. Double check and make sure that your pop-ups aren't blocked. And then on my computer personally, it pops up in Microsoft Edge. So just make sure that it might not pop up in Chrome, it could pop up in Edge Explorer. Okay. So first off, we would always like to thank our sponsors. Our Tier 1 leaders, Carrier, Con Edison, WSP, CDE, SRS, Train, and Fulcrum Group. Our Tier 2 partners, Train and Fulcrum Group, Goldman Copeland, Tech Systems, JB&B, Mitsubishi, AKF, Cisco, ABE, Fleet, Technical Air Systems, Olimo. Our Tier 3 supporters, ADS, Chimney Design Solutions, Federal Pump, Schneider Electric, Johnson Controls, National Air Filter, Tolic, Cerami, Wallace Ennis, Siemens, Daikin, Thermal Systems Associates, Automated Logic, EcoCare Corp, Skyline. Oh, and Belimo. I apologize, they're not on here for some reason, but they are a Tier 3 supporter. Upcoming events for ASHRAE. This Thursday, we are having our second in our designer series, Lunch and Learns. That is going to be on fire and smoke dampers in healthcare facilities, and that's going to be given by Henderson Engineers. And then we have four additional designer series coming up in the end of April and beginning of May. And then 2 more dinner meetings. The dinner meeting will be early in May. We're holding the 5/12 date, which was our original in-person dinner meeting because of the Memorial Day holiday. And that'll be on electrification, and that's going to be given by Mark Cracken. Okay, I'm going to turn it over to Duncan Phillips, who's our speaker for the evening. He gave this short presentation in the Winter Design Conference, and the board thought it was very interesting and wanted him to come and expand on it. So we'd like to welcome Duncan from RWDI. One second.
Thanks, Natalie.
Yes.
You can hear me okay?
Yes, I can hear you just fine. And
Perfect.
oh, one other thing, in case there's any issues, I will be looking at the questions portion of it. So if you have any issues or questions during the presentation for our Q&A section, please just use the questions box. All right, changing it over to you, Duncan.
Thanks. So, Natalie, just confirm, have you got my screen up?
Yes, you can see your screen.
Okay, so welcome everybody. My name is Duncan Phillips. I'm a principal at RWDI. And it's my pleasure to sort of take that ASHRAE presentation that was done in February, early February, and sort of expand it. And what you're going to see here is sort of, we're going to talk a little bit of the original physics, and I'm going to sort of help maybe describe and distort your understanding of how stack effect gets set up. Stack effect does not get set up because hot air rises. I'm not going to deny that hot air is lighter than cold air, but that's not actually the reason why stack effect gets set up. So we're going to sort of talk about those kinds of things and then take you through some case examples to sort of in real buildings so that we can sort of elaborate on that. I have two examples, and depending upon how we're doing on time, I might stretch out a third. We'll see how that goes, but I'm planning on landing this a couple of minutes before the hour so that there is a chance for questions and I can stick around beyond 6 o'clock if people still want to chat. First thing people ask, is this live? Yes, it is live. I am not a robot, and that's just proved the point. The other thing is that the AIA does offer credits for this. If you are an architect and need AIA credits, they are eligible for this presentation, but the AIA just wants you to know that they don't endorse anything I say, which is probably very wise of them. And then in terms of our learning objectives, what I'm hoping to do is be able to sort of communicate that understanding of the physics of stack effect. And we'll talk about some real world examples and design strategies that you might be able to use in the future, and a set of design ideas for future projects. And I suppose this is where we start to have that philosophical conversation about, is stack effect an architectural problem or a mechanical engineering problem? And given that we're at ASHRAE, the majority of the people listening in are going to be engineers. I have seen some mechanical engineers basically sort of refer this to being an architecture first issue. And it is true that it has to do with the height of the building, and the way in which mechanical engineers can help contribute to it is to make sure that the systems are able to deal with the pressures. And I'll show you some of those issues as we go forward. Also, what's important to me is just to acknowledge that I get the privilege of working with some particularly brilliant people at RWDI, and they teach me things every day, and we get to work on cool projects. And so what you're going to see here is the collective work of many people back at my firm. So let's sort of just jump into a little bit of background in terms of places where I've been involved in working on projects. So you sort of see three columns here. On the left-hand side, heating climates where we have heating issues. Cooling climates are in the middle, so that's some people refer to that as reverse stack effect, and I will talk a little bit about reverse stack effect, but you'll notice that the list is almost identical, and in most cases, buildings experience both heating and cooling stack effect, and I will show you a couple of differences. When you're dealing with a cooling climate, so summer stack effect, the mechanisms that we might use in winter mode actually work against us in summer mode, and I'll show you a couple of examples of that. And then the far right-hand side is existing buildings where we've gone in and sort of taken measurements and tried to deal with a building that's gone up that has a stack effect problem. In a few cases, what actually was originally manifested as a stack effect problem turned out to be a combination of stack effect and HVAC or stack effect and wind. And so it's not always clear until you start to pull apart the building, if you will, figuratively, to learn what's driving the building's problems. So in terms of an outline of what we'll talk about what stack effect is, the driving forces and the impacts. We'll talk about locating the neutral plane, because that's actually very useful for a variety of things, including natural ventilation. We'll talk about the influence of building pressurization. So what does building pressurization do? And then managing stack effect, and we'll use case studies as we go through. I should note that I'm trying to be bilingual on our units. So there will be places where I think I've got every spot that there are IP and SI units, but if I slip up and I miss one, 50 pascals is the same as 1 pound per square foot, 250 pascals is the same as 1 inch, and 1 inch is about 5.2 PSF. And there's a little bit of rounding going on there, but those are basically the numbers. So 1 inch is 250 pascal, 1 PSF is 50 pascal. So let's talk about what it is. It's a stack effect is a phenomenon that exists in all buildings, and it's induced by the differential pressure force originating from an indoor-outdoor temperature difference. So this plot is sort of clearly gratuitous. In the winter, air wants to come in at the bottom and leave at the top. That's useful when we're starting to talk about lower-rise buildings where we're trying to naturally ventilate. And usually when we're naturally ventilating, the interior space is slightly warmer than outside. Even in a hotter climate, this is usually true. And so air wants to come in at the bottom and leave at the top. And it's that delta P that's created by the indoor-outdoor temperature difference that starts to drive this force. The issue with stack effect, though, is that there's really sort of a driving force, and it's very difficult to get rid of the driving force. And we will talk a little bit about how to get rid of that driving force. And when we start to talk about design, what we're trying to do with design is to manage the severity of the impacts and to make sure that the design doesn't actually enhance the problems that are experiencing the stack effect. So usually what ends up happening is we get asked by clients, how do I get rid of stack effect in my building? And that's a legitimate question, but it's better phrased, how do I reduce the frequency of it, and how do I eliminate the adverse impacts in my building? Because remember, stack effect for natural ventilation is a good thing. So here's an example of a building in Denver. It's 44 stories, approximately 550 feet. And on the day of the video I'm going to show you, it's about 10 degrees Fahrenheit outside, 70 inside. In terms of our sort of language, this is moderately tall and it's not a particularly cold day. So in this video, what ends up happening is these three guys start to open the door. So I'm going to sort of stop it for a moment and just sort of highlight a couple of things. When this door gets opened, you'll notice it's a fairly big burly guy. He pushes it open, but it's hinged about here. The door is not hinged at the very edge, at the right-hand edge. It's hinged somewhere along. We would refer to this as a pressure balanced door. And what's happening is that the force on one side of the hinge is offsetting the pressure force on the opposite side of the hinge. So it's the overall force to open that door actually becomes less because of the way in which that door is hinged. The other thing to note is that the kind of flows that we're getting are significant. And so often people will talk about, well, you know, why do we need a rotating door? They're awkward to get in and out of, and it's true. They are more complex to get in and out of. If they're designed well, they actually work really well. But what ends up happening is if we don't have a vestibule, we don't have a mechanism to control stack effect, all of that cold air that was outside at 10 degrees Fahrenheit has just come in and swamped your lobby, and you don't have comfortable guests or residents anymore. And now all of a sudden we're into a much, much bigger ventilation system. So there are a variety of potential impacts. These include things like whistling airflow through doors and cracks, difficulty opening and closing doors. I'll show you an example later on where I've been in cases where it didn't feel safe opening and closing a door. Difficulty controlling temperatures on some floors with excessive infiltration. So there's an example with that door where that fellow opened the door and all that air's coming in. There are cases where we've seen that buildings could not keep themselves warm in the winter. Elevator door and operability issues. And what we mean by operability issues is the doors won't close. My experience on this one is that at the bottom of the building where the force is coming in and pushing into the elevator shaft, that tends to be where elevator doors fail the most often. It's at the bottom of the building in winter where air is pushing into the shaft. I've seen at the top of the building nearly an inch of water pushing out on an elevator door, and that elevator door working just fine. So when I sort of talk about criteria, that one's a bit awkward because we do have criteria and thresholds for elevator door operability, but it depends upon which way the pressure is working on the door. And then, of course, the last thing is whistling. I'm sure everybody who's online has heard elevator doors whistling as a result of stack effect driven flows. There are increased building energy costs associated with uncontrolled airflow to the outdoors. And that has to do with all that excess infiltration that's going on. There can be an ingress of odors between the outdoors, but also an ingress or migration of odors from one unit to another. One of the examples I'll show you had toilet exhaust leaving the toilet, it had odors leaving the toilet exhaust and entering into a different unit. And this happens to be cigarette smoke and sort of causing some concerns and quite frankly a degradation in the enjoyment of that unit. So as you can imagine, the residents of that unit were a little irritated. So often that unit-to-unit odor transport, though, is not only driven by stack effect, but it's also driven by wind. So this is back to how do you set up your ventilation system, the risers and the ductwork to manage the pressure forces that are get created by wind and stack effect together. So this is the moment where I break your knowledge and sort of talk about why stack effect gets set up. And I'm going to use this with an example of a tube of water and a tube of air. And in this particular example, what ends up happening is that the tube of water and the tube of air are sitting side by side, and you know intuitively that the tube of air is lighter than the tube of water. And now I'm going to connect them. And the process of connecting them, you know that what will end up happening is that this water will travel this way and the air will travel that way. And the reason that's happening is not because the air rises. What's happening is that the weight force of that tube of water is heavier than the weight of the air in the other tube. And so it's just going to flip around. Now, if you think about it, now what I've said is that we infinitely sort of cool this. So all of this water coming out here is instantly turned into water, or in the building example, the hot air is instantly turned into cold air because we just have a massive outdoor reservoir. The water that was coming into the air tube, which is outside cold air, is coming into the building. The HVAC system takes care of that and warms it up. So the system gets set up where we have this infinite loop where outside we're always cooling that air that's escaping, and inside we're always heating the air that's infiltrating in. Buildings are a little bit more complex than this, but this is how it gets set up. It's because the weight of this column of outside air that's cold, in the case of winter, is heavier than this weight of air here. And the best way of sort of showing that is that with this example, I've got a 1,300-foot building. Outside it's 0 Fahrenheit, inside it's 70 Fahrenheit. And the mathematics on the two columns here are just describing the mathematics. So we sort of can calculate the weight, or the density, sorry, of the air mass inside and outside. And then we calculate the height of that density of air, which then gives us a pressure force at the bottom of that column. So this is where that pressure force comes from. This is where that 14.6 psf comes from. Is it's from the difference in the weight of the columns of air inside and outside. Now, what ends up happening is that this is the total pressure force difference. And so that ends up getting distributed. And what we've sort of suggested here is that of that 14.6 psf, approximately 7.3 is at the top and 7.3 is at the bottom, which implies that the neutral plane, or the point where we have 0, is somewhere in the middle. And we'll talk about the neutral plane in a moment. When we go to summer, the summer is going to be different. And what ends up happening is that for the same building with the same sort of reasonable set of temperatures outside and inside, what ends up happening is that we've got a 4.2 psf pressure difference, not 14. So in the summer, the pressure forces that we have are a lot less. So let's go back and talk about, no, I'm sorry, I'm just sort of trying to point here that the neutral plane is approximately halfway up in this particular example that we've used. We will come back to that. Let's go sort of talk about a few example buildings. These are showing some buildings that you will have heard of. And what we're looking at here is temperature on this scale and the occupied height of the building here. And there's some buildings that you know very, very well. So the Burj Khalifa in Dubai, it gets cool. And you'll notice that because of the height of the building and because of the outdoor temperature can drop to just below 60 degrees Fahrenheit, that it ends up having what we're sort of referring to as a moderately strong stack effect force. Whereas when we get up to something like Willis Tower, it's very, very strong. It's actually severe. This is something like, you can have a couple of inches of stack effect force set up just strictly by that indoor-outdoor temperature difference. And the strongest stack effect force that we've ever been involved in had a 4-inch delta P inside to outside. And again, when I talk 4-inch delta P, I mean that when you look at what's happening at the top has got 2 inches and the bottom has got 2 inches. If this is the building height and this is the pressure that we're the delta P inside to outside. So that's the strongest we've ever seen. Over here in summer, Burj Khalifa clearly is winning just because, again, it's taller and it's a lot hotter, but you can sort of see that these buildings over here are candidates. That building in Denver that I showed you, for the conditions that exist in Denver, isn't a particularly strong, doesn't have a particularly strong stack effect. In terms of its severity, it's about the same as Burj Khalifa. It's in the same class. And the building in Denver just doesn't actually show up in this plot over here. And that's because the temperatures don't get hot enough in Denver to show up on the plot. So I had been talking about something approximately 14 PSF on that building, that example building that we were just using. This is kind of like what 14 PSF looks like. It's an inflatable dome where you might go and play some sort of sport. And so if you look at what goes on in these buildings to control that pressure, what you have is you have some very well sealed doors. It's made of steel. Yes, there's windows, but they're clearly part of the steel package. So this set of doors here and even the rotating door are very, very good. Whereas if we sort of look at what we do architecturally in buildings, this is sometimes what we see at the bottom of a building that has strong stack effects. It just isn't going to manage stack effect the same way. And so that's why all of a sudden stack effect problems leak into the middle of the building. If you sort of want to put it into reference, 350 Pascal or 1.4 inches, that's really what we're talking about, on a door would require that you pull on the handle with approximately a 100-pound force. That's what it takes. And the way you get to that calculation is you sort of have a pivot point, you have a door, you have a handle that you're going to pull, and then you have a pressure force on that door that is acting uniformly across that door outwards. And that's what the force is that you need to put onto this door to start it moving. So the stack effect forces can be serious. So let's talk about how we judge problematic for a moment. There's a variety of thresholds, and often this is about how irritating is stack effect and then the severity of it. So one of the thresholds that we use is an operability threshold for a door. And if you sort of look at NFPA says 30-pound force to set it in motion. That's between 100 and 130 Pascal or 2 to 2.7 PSF. That's the kind of pressure that would be allowed on a door to hit this as a maximum. That's different from ADA, where that is about talking about an egress path, and it's a much, much lower pressure. And that's why most buildings have a power door, is that managing stack effect to get a 5-pound force on a door is virtually impossible. So the power paddles are absolutely necessary, whereas a 30-pound force is something that we should be able to manage on most doors. We then have elevator door operability, and we usually talk about 0.5 PSF or a 1/10 of an inch. Whenever we see a number above a 1/10 of an inch on an elevator door, we start to flag that as a risk. And that simply has to do with the variability of elevator doors across the planet. And it is difficult to judge because I've seen, as I said, I've seen a door with nearly an inch on it pushing outwards, and the elevator door was working just fine. I've seen doors with pressures at approximately 0.4 of an inch pushing inwards, and it was fine. It was whistling like crazy, but it was fine. So elevator door operability is that we sort of start talking about it at 25 Pascal. And one of the examples I'll show you had exactly this issue. We then talk about whistling through doors, and whistling through doors is not so much the pressure, it's the flow speed and the flow velocity. So if you think about a door jam for a moment, and this is like a zoomed in view of a door jam, and you have a door that's sort of sitting here, if the pressure is pushing the door this way, it's sealing it. So that actually helps to crush the door against whatever jam we have here, sorry, whatever seal we have there. However, if the stack effect force is pushing the door open, that will tend to push this away from the seal, and so all of a sudden air can start to leak in here. And what you have is you basically have depending upon what kind of door you have, you could have in here a little resonance cavity where the latch goes, or you could have two planar surfaces where you can get a harmonic wave set up. So there's all sorts of different mechanisms that whistling can get set up. And usually we refer to a flow volume rather than the flow speed, because it really does depend upon what type of door. Is there a hole for the latch? Is there roughness? What kind of seal is there? But one of the things that we find is that people forget that what ends up happening is if this door is pushed away from its jam, often many seals start to fail. And then in terms of another criteria, there's sometimes difficulty just balancing the HVAC system, or an inability to deliver fresh air to some areas. And so we'll talk a little bit about that too. In this particular example, I will come back to this image a little later on, but what we're looking at here is the floor plan for a typical building. This building happens to be 1,300 feet tall, and all we're flagging here is that the pressure on the facade is much, much higher than that threshold that we would have for being able to operate this door. In SI, this would be 130 Pascal. So we're nearly 3 times higher than the criterion for being able to operate that door. And then in terms of the elevator doors, they're 37 Pascal where we want 25. So these are also a problem. So we'll talk about this example about mitigation in a little bit. When we talk about elevator door operability, this is what we mean. The inner doors on the cab are closed, so they work fine. They actually don't see much pressure at all. It's these doors, the floor doors, as they're starting to close in, what happens is if there's a high pressure on this floor and there's a lower pressure in the shaft, as more and more of this door gets exposed, there's a higher and higher greater force pushing in, And usually what ends up happening is the runners start to bind, or they're just not flowing smoothly in the track, and the door senses that something's in the way and then stops working. And then we've seen people, some elevators that actually have a guard sitting there, and their job is to make sure these doors close. So one of the consequences. And I had sort of flagged that sometimes we see problems with buildings just not being able to heat themselves, and clearly it's about cold air ripping in through the course of the day. And sometimes this cold air is not necessarily coming in through open doors. It could be just leaking through really, really poor doors. And I'll show you some examples of some poor rotating doors in a little bit. Hope someone's keeping track of all the things I promised to do by the end of the seminar. And then when we talk about cold air coming in at the bottom of a building, that's sort of has a similar analogy to a hot climate or summer condition, where we have hot air that's infiltrating at the top. And so, personal story here, I was in Dubai. I was on a treadmill at the top of a building, and people kept going in and out to go to the pool deck, which was on the top of the building. And every time someone opened the door, 100-degree air came blasting in that was very, very humid, filled the gymnasium up with that kind of air, made it very difficult to work out. The ventilation system tried to catch up, it would get it back down to something that was reasonable in the upper 70s, and then poof, someone would go out again. So that condition exists both in hot and cold climates. So let's talk about what and where the neutral plane is. And I think most people are aware that the neutral plane is where we define the indoor and outdoor pressure to be the same. So the delta P is 0. So when I start talking about delta P, what I mean is the indoor and outdoor pressure difference, and indoor minus outdoor. So if the indoor is higher, it will be positive. If the outdoor is higher, it will be negative. And so in this particular example, I've got a building with an opening at the top. This could be a pool deck. This could be some sort of terrace. It could also be a vent at the top of an elevator shaft. And what ends up happening up there is, because there's no obstruction between the inside conditions and the outside conditions, the delta P by definition is 0. So the pressures are the same. And as I come down, and this is now a winter scenario, as I come down, the weight of the air in the shaft is heavier, and therefore the pressure gets higher faster. Whereas when you come down the inside shaft, what ends up happening is, because the weight is less dense, the increase in pressure as we come down is not as great, so I don't get as higher pressure here. When I do that subtraction of indoor minus outdoors, I have a negative pressure, and that's what this is showing. So I have air that wants to come in at the bottom of the building. When I open the bottom of the building up, same deal. The door is wide open. The pressure at the bottom, therefore, indoor and outdoors has to be the same. And as I come up indoors, because the weight of the air is less, it doesn't drop as much as the heavy air outside. And so that's why I have the outdoor pressure dropping a lot faster, is because the outside air is more dense. So again, we do an indoor minus outdoor pressure difference. And so because the indoors is heavier, air, the result is positive, air wants to leave at the top. When we actually look at a real building, what happens is there are distributed openings all the way up and down the building. And so the neutral plane is somewhere in the middle. Usually, we would sort of pick in a neutral building, a passive building where there's no ventilation system and there's no wind impact. We would typically see the neutral plane being somewhere about the 45% height. And the reason it's not roughly at a halfway height is the neutral plane is actually affected by the size and the types of openings. So if you all of a sudden put a door down here and you only have operable windows as you go up, what will happen is that the presence of this door will drag the neutral plane down a little bit. So if you sort of assume that the neutral planes are roughly at the 45% height, it's a good starting point. But in this case, I've just assumed it's at the 50% point. And the slopes on this curve and this curve are the same. So I haven't changed the slopes because that's just the change in pressure as we go up and down. And then when I do an indoor minus outdoor pressure difference, I got negative at the bottom, air wants to come in, and I got positive at the top, air wants to leave. That's why that's set up. And you can do all sorts of mathematics to sort of prove this to yourself, be comfortable with it, but that's what I found is the best way of describing how stack effect gets set up and why those indoor-outdoor pressure differences are the way they are. When we talk about summer, what ends up happening is the slopes of these flip around, and when we do that indoor and outdoor pressure difference, what ends up happening is indoors is negative relative to outdoors, so air wants to come in at the top, and air wants to leave the bottom. And that's that sense of a hot condition where you have it reversed. When we start talking about natural ventilation can take advantage of stack effect. And in this particular case, what I've got sort of a building set up where we have a chimney, and this chimney, the act of having this opening up here lifts the neutral plane up. The outcome of that is that the neutral plane, let's say, could be up here. In order to get natural ventilation to work in this building, for these two rooms here, the neutral plane has to be above this opening in order for air to come in. If the neutral plane is not above that level, air will leave that opening. So when we sort of talk about the overall natural ventilation in this room is isolated, so it's only got air coming in, probably wind-driven, and air leaving. This room is single-sided. I've got air that wants to come in here and leave there. It sets up its own neutral plane within itself, and again, it's isolated from the rest of the building. So this single-sided ventilation works. But in this case, for these two rooms, because they're working together and they're connected to a chimney, we have to manage where the location of the neutral plane is. If we close that lid, what will happen is the neutral plane is now somewhere around the halfway point between the two openings, and air will come in here and leave there. So if you're designing a natural ventilation system, it's really important to make sure that you can control your neutral plane. If you're trying to design, let's say, an atrium, and I've seen this done before several times, where someone's designed a building, they put a lovely large atrium on it, and they say they're going to bring air in at the bottom, and they have air leave at the top of this atrium. The air is going to rise. Of course, these are well-behaved arrows. And then on every floor, as you go up the building, they will say, well, I'm going to have air that's going to come into this floor and air that's going to leave this floor. Air that's going to come into this floor, air that's going to leave this floor. That's rubbish. It doesn't work that way. What will happen is that air will come into these floors on the lower half, below the neutral plane, and then above the neutral plane, air will leave. That's actually how it's going to work. So you got to be really careful with your neutral plane and understand how the flows are going to go in the building. So now let's talk about the effect of building pressurization. By pressurization, what I mean is that the net flow being pushed into a space is greater than the net mechanically removed flow. And that difference, either positive or negative, is going to contribute to the perception of stack effect in the building. And so overall, the HVAC system is contributing to the net pressures within the building. In the case of this example that I showed you earlier on, so I'm going to use this example again, where the neutral plane still is at the 50% point, roughly. When I sort of take that building and I start to add pressure, so I'm pushing pressure into the building, and the assumption here is that every single floor is getting a little bit of pressure. What happens is that this line where I used to have my pressure difference is now pushed this way, and this difference is actually the amount that the HVAC is pushing in. So that's what ends up happening when I pressurize a building. And so you'll note that the force at the bottom, the pressure at the bottom has significantly dropped, but the pressure at the top has significantly increased. And so often what people sort of think is, well, I'm going to control stack effect by adding some air in the lobby, without realizing that nothing's for free. The pressure has to increase at the top of the building, and increasing air only in the lobby floor may actually create other problems, and I'll show you that in a moment too. In the summer, so remember the line goes the opposite way, and I have air that wants to come in at the top and leave at the bottom. When I pressurize, I still push that line this way, and now all of a sudden what's happened is I got a significantly greater force at the bottom of the building than I did before I started pressurization. And this is that example where I had said what we do for winter stack effect to try and manage stack effect can work against us in summer. And here's the example. In a typical building, office or resi, it doesn't really matter. What ends up happening is that the bottom of the building is often very, very leaky relative to the top. And so as a result, all this extra pressure at the bottom is likely to cause a significant outflow at this building. So in this particular case, you may be better off trying to just gently pressurize the building a little bit on the floors, but not do so in the lobby, because that lobby is going to see an outflow anyway. The other thing to note is that if you happen to undersupply building, so let's say you have a residential building and you have toilet exhaust, dryer exhaust, kitchen exhaust, and you're centrally supplying makeup air, but you don't have enough makeup air, the building will go negative. And so if the building goes negative, what ends up happening is this is the new curve, and this is the force at the bottom of the building. And remember, air wants to come in this particular case. And so what's happening is a lot of air coming in at the bottom of the building to feed the fact that the building is negative from an HVAC perspective. People perceive this as a stack effect problem, and it looks like a stack effect problem, but it's actually associated with the HVAC system. So you got to be careful when you try and diagnose these problems, not to sort of fall into a trap and sort of just taking some measurements and being done. I have an example of that too. Sure, I'm getting a long list of things I promised to talk about. So here's an example of a real building where we were looking at the pressurization rates in it and where the location of the neutral plane is. This building's in the Midwest US. The outside conditions were about 32. The inside was somewhere around 73, 74. And the occupied height, so the highest point of the building, 790 feet. This blue line here, the first blue line here, is what we would expect with the neutral plane at the 45% point. So this is what we would refer to as the passive building. There's no ventilation in that passive building. It's just sort of sitting there. It's just warmer than outside. And forgive me, sorry, these units here are Pascal. So remember that this here is 1 inch. This here is 1 PSF. So this is what we would expect. And these were the measurements that we were getting. These lines are the measurements that we were getting for all the different setups of the mechanical makeup air systems. And so the makeup air system here, we have two of them, one on the upper 2/3 of the building, one on the lower third of the building. And we're setting them at sort of 50% of their regular supply rate, or sorry, 50% of their max, 35% of the max, and toying with different parameters. And one of the things you should note is this pink line, we actually managed to make the entire building positive. So we made it so that air was actually leaving the lobby front door. But the consequence of that was that we had over 1 inch acting at the top of the building, pushing outwards. And at the top of the building of this residential building, if a unit occupant opens up their window, and when it's 32 degrees Fahrenheit outside, it's not unreasonable, people will. If they open up their window, all of a sudden their unit door is taking all of that force. We cannot rely upon the elevator doors taking much pressure. In that case, the unit door takes all that pressure. 250 Pascal or 1 inch of water on a unit door is a significant pressure. And in this case, these unit doors were about twice the regular size of a normal door. So the force on this was enormous. But here's an example of playing with different pressurization rates to try and figure out a sweet spot for where this building should be operating. So now let's talk about managing stack effect. And so again, we're back to what's the design goal? And the goal is to reduce the frequency and severity of undesirable impacts. It's not necessarily to get rid of it. I'll talk about how to get rid of it in the end, but it's going to be a different discussion. So my example problem is an 80-story building. It's the 1,300-foot building that I keep moving along. And it's in a very cold environment. And we're going to talk about two different types of mitigation. One's passive, where it's sort of tighter building envelope, better doors, vestibules, revolving doors. And then there's active mitigation, things like HVAC pressurization. And by HVAC pressurization, hopefully you saw earlier on that we really do need to have seasonal control. The pressurization you set up in the winter should not be the pressurization you set up in the summer. So here's the example. This is, again, we've got approximately 6.2 PSF acting inwards. We're looking at the lobby. So think of this as the lobby of a hotel, a tall hotel, or a mixed-use building. And this pressure on the facade is acting also on the doors, and that exceeds the operability threshold of 130 Pascal, or 2.8 PSF. When we go to the elevator doors, I've already pointed this out, but this is 37 Pascal, that's higher than our threshold. So this is with no mitigation. So the first thing is if we improve the facade, so what we do is we tighten up the facade, and we say we're gonna make the facade better. The pressure has gone up on the facade. So now all of a sudden, my pressure's gone up. So the facade is doing more work, which is great. The elevators are now seeing less than the criterion, so they're at 0.4 PSF, so that's good. So they're under control. The elevators will work without a problem. But I've still got a problem on my operable doors. These doors will still have a problem. If I put vestibules on those doors, the vestibules will help, but because of the strength of the force on the facade, sort of a double vestibule isn't going to do it. You'd actually need to put 3 doors in a row to bring each door below the 130 Pascal pressure requirement. So a vestibule here isn't going to be the only solution. you could positively pressurize the lobby. So when I had talked earlier on, that often what we do is we stick in some extra force or extra pressure in the lobby. If you do that, you will increase the pressure in here, which is phenomenal because you've solved the problem. All of a sudden, the pressure force is now significantly less, but you've moved all that pressure to the elevator doors or to the building up above. And so nothing is for free. And in this particular case, the total is still the same. This roughly 140 Pascal and this roughly 200 Pascal is still the 340 Pascal that we were talking about being there originally. But what's happened is, if you sort of look at this from a overall building perspective, if this was the pressure line before, where this is height up here and this is delta P here, if this was the approximately, let's call it sort of, what I say, about 340 Pascal. If this was 340, before what we had is we had the facade taking this much and the elevator doors taking up this much. Now with this method, you use the HVAC system to force air into this floor, and now all of a sudden the ballooning is not happening here at the facade anymore, it's happening on the elevator doors. So if you then, instead of pressurizing the lobby, you pressurize each of the floors a little bit, what ends up happening is you even that out, and now all of a sudden the elevator doors are happy, as is the front doors, and all that's happened is there's been a little bit of positive pressurization on all floors. So this is a much, much better way of doing it. The reason why you might go and positively pressurize or put a lot of air into the lobby is to deal with the infiltration, but that doesn't mean you have to positively pressurize the lobby. You could actually just put that on recirc. So adding a little bit of pressure on all floors is actually a better way of going. So the challenge with mitigation is that this is kind of like trying to plug a leaky dam. When you try and manage stack effect, if you're going to go and seal a hole or put a better door on here, you really do need to make sure you get all of the holes in the facade or do better doors everywhere. The analogy here is a water balloon with sort of little holes in it. A better analogy, this past weekend, I was out trying to seal the fence up to prevent little bunny rabbit from getting into the veggie patch. That's the better analogy. That little bunny is going to try and get in any single hole that you happen to have in your fence. And if you put a lot of effort into one hole, the bunny will find the other hole. It's the same thing with stack effect. You've got to even out your effort so that you cover all of the holes well, rather than focus all your effort on one. So the example of the analogy to stack effect is don't just focus all on the front door, because if you fix the front door, the problem could arise somewhere else. So the challenges with mitigation is it also depends upon where you are and what kind of buildings you have. So if you have an office building, you get a high occupant traffic during rush hour. If you have a residential building, the residents have operable windows and maybe doors and exhaust vents. And the operable occupant behavior of leaving the windows open means that your facade is immediately compromised. So you have to have a backup, assuming that your occupant is going to leave their windows open. If you have a mixed-use building, then you have different types of owners and different operations. And usually what ends up happening is we have a layered approach where we have retail at the bottom, we may have an office in here, we have hotel, and we have resi. Ideally, it would be the other way around. It should really be retail at the bottom, hotel, resi, office, where the office is at the top of the building, because usually it's tighter. But there's many codes in many jurisdictions, New York being among them, where you cannot do it that way. You cannot have office above resi. So, and then of course, at the bottom of a building, you could have a podium, and the podiums can connect to subways and shopping and things like that. So often, the bottom of a building is incredibly porous. So this makes it a bit of a challenge. So let's talk about some example mitigation of buildings that you're probably aware of. This is the solution to an airlock solution where you walk in through one door, that door closes, you sit and wait, and then the outer door opens for you and you pass through. This is because the owner didn't want to have rotating doors on their building. We've also seen cases where the rotating doors are part of the problem. In this particular case, you can see that there's a drip tray, and this drip tray can actually be a source for air to sort of come in, leak underneath the drip tray, and come out the other side. So when you're speccing a rotating door, it's really important to make sure that you spec it so that this door actually holds the pressure, and that the drip tray is not part of the problem. And that has to do with how the drip trays are arranged under here and what the pipework looks like on the drainage side. We've also seen cases where doors have been used and sort of proudly inserted, but the concrete that was poured had a little wow in it, or in this particular case, the doors just aren't long enough. No one bothered went to put in anything at the bottom. So this door is not carrying much pressure at all, even though it is separating the garbage area and the outdoor loading dock from the interior of the building. And then this is a famous building. I won't mention it, but when I was there a few years ago, you can actually see daylight underneath the door. You can see gaps between the door and the hub. But later on, they sort of went and sealed that up, so it actually got a lot better. But this is an example of a rotating door, again, where the spec for the rotating door didn't really think about stack effect. It was just a way of managing people and security. So I'm going to now talk 2 case studies. One of them is a building in Shanghai, and this particular building is a 40-story office building. It has operable windows, and it's got 3 lift cores, or elevator cores. And my apologies if I occasionally switch into using the word lift. It's just shorter and more efficient to say. So we have 3 elevators, 3 elevator cores, a high, a medium, and a low elevator core. And all this sort of diagram is trying to say that the low-rise elevators touch all of these floors, the mid-rise touch all of these floors, and the high-rise touch all of these floors, and the service elevator touches all of the floors in the building. And the issue here was that the high-rise elevators on the ground floor would not operate when it got to semi-cold, and semi-cold being 40 degrees Fahrenheit. The elevators just wouldn't run. What would happen is that the doors would seize down on the ground floor. And so what the building operations did is they actually kept 2 of the high-rise elevator lobby doors open. And so the way that worked was they had an elevator bank here with 3 cabs on this side. And then they have an elevator bank over here with 3 cabs on this side. And at the top of the building, these 2 sets of elevators shared 1 machine room. These were the high-rise lifts. And so what they were doing is they were forcing this door to remain open and this door to remain open, which meant that the delta P between the lobby and these elevator shafts was effectively 0 because these doors were always open. So that was their solution. But what they needed to do is, because they were trying to hand the building over to the owner, the developer wanted to give it to the owner was saying, well, I can't use all my elevator shafts, I don't want the building in. So they had us come in and we went and took some measurements. And what you're looking at here is the measurements on the high-rise elevators across the elevator door. On the lobby level, this one, this is the high-rise in the lobby, this is the mid-rise lobby, and this is the low-rise lobby. And then these were the pressures on the upper floors where those doors happen to touch. And you should note these are all in Pascal. This is running over 40 Pascal, where we've said that the threshold is somewhere around 25. These doors were operating just below 40, but they were not running into a problem. And then the low-rise lifts just were operating just fine. So we sort of knew at this point that the threshold, the operability threshold, was being exceeded. When we sort of did a little walkabout and had a look, you can see this is the shroud of the rotating door at the front. This is the door itself that's rotating. That's the gap. This is the gap underneath the door. This is the door itself, so it's not closing very well. So there's an awful lot of leaks. Took a thermal camera around, and we would expect to see this line. This is the mullion. We would expect to see this line. It was the mullion. We would not expect to see these plumes. And those plumes were essentially leaks in the facade. So what that ends up meaning is that we have a very, very leaky facade. When we actually measured the pressure on the facade, we were getting a lower pressure being taken up by the facade than we were the elevator doors. That's a problem. So in this case, we have 2 options. You can either seal the facade, which would do it, but there's no guarantee. I'm back to my bunny rabbit example here, where you've got to be able to seal every single hole in the facade. Otherwise, it's not worth sealing any of them. You could seal all but 1 hole in your garden fence, but the bunny rabbit will find that one way into the veggie patch. So you either seal all the facade or you don't bother try, and that would mean wrapping this place with a saran wrap. The other option was to create a vestibule for the high-rise lifts, and there's no guarantee that this would actually be a solution. We actually went and had a look at what would happen if we put a rotating door vestibule on so if we put a vestibule on this, and what would end up happening is if we vestibuled the high-rise lifts, it would actually increase the mid-rise lifts, and all of a sudden the pressure here would go up because we'd solved this problem, but the problem is transferring somewhere else. That would then end up meaning you'd need a vestibule in both the high-rise and the mid-rise elevator. So all of a sudden you're into double the cost that you were anticipating. So the solution in the end was, given that they were actually already operating with leaving a door open, the solution was to actually put that into place in a more formal but hidden mechanism. So we actually advised them to put in a bypass. So they actually knocked a hole in the elevator shaft wall, hid it, put dampers on it so they could close it in the event of a fire. And what that meant was that they were building in a bypass around the elevator so that they didn't have to worry about the elevator door taking up pressure. It's not a standard approach, and in North America there may be some issues with it, but this actually did solve the problem for this particular client. So let's talk about another example. And this second example is in the Midwest US, and it's a building that had a range of challenges, and that included that under not very cold conditions, so 32 degrees Fahrenheit, it was experiencing strong sack effect problems. The elevator doors were whistling. They had significant flow entering the front doors and into the elevators. They had trouble keeping the front lobby space warm. There was a transfer of cigarette smoke between units via the toilet risers. So the toilets were a source of smoke odor transport between one unit and another unit. There was difficulty closing the elevator doors, and they had high pressures on some unit doors. This building had operable windows on all floors. It had centralized makeup air to the corridors, centralized toilet exhaust, and it was net positive. So just in terms of the way the elevators stack, there were low-rise elevators that shared a shaft that actually shared their shaft with the service elevator. And so that immediately means that this service elevator is compromising our ability to segregate the building, so there were no zones. And then the high-rise shafts shared their own shaft. On the amenities level, all of the elevators in the building touched the amenities level, and then the upper part of the building had just the high-rise elevators and the service elevator touching it. When we went in and measured that delta P, so this delta P is running from the outside of the building into the core, into the elevator shaft at the bottom of the building, and from the outside of the building in the core of the shaft to all the way to the outside at the top as well. Sorry, this is meters and pascals, my apologies. So what we would expect was this red line, and what we measured was this green line, and that's the pressurization in the building. So we sort of anticipated that, so that's okay. But what we are measuring in terms of the totals, the total delta P that we were measuring across the building was similar, so within a reasonable amount of error. What we did note though is that when we were measuring this pressure at the bottom of the building, the facade was only taking up 1/4 of what the elevator doors were doing. And this was because the lobby was being pressurized directly. And if the lobby is pressurized directly, remember that I showed you that example earlier on, what it does is it shifts the forces to the elevator doors and takes it away from the facade. So that was part of the challenge with the elevator doors not working. At the top of the building, when we're way up here, we were getting very strong pressures. The facade was taking up most of the pressure, 165 pascals, so over half an inch, nearly coming up on 3/4 of an inch. Whereas the elevator door is almost zero, and so the facade was doing the work. The elevator door was not taking up any pressure. However, when the facade opened up, so at this particular level there was a door to the outside, directly to the outside from the elevator lobby. When the facade door opened, all of this force was immediately transferred to the elevator, and so that meant that elevator door had to take an awfully large pressure. This was the example of the elevator I had that would take an inch because we bumped up the pressure in the building to see what would happen elsewhere. So, and then the neutral plane was at the amenities deck. And so when we sort of think ahead and think about the ASHRAE 0.4% temperature when it's really cold, it's on the order of -1 Fahrenheit, the kind of forces that we would see across this building would be nearly 2 inches. And so 2 inches across this building would be enormous. And again, if we sort of look at the ventilation system working on it, this is what we would expect as the neutral plane location, but given the ventilation system is operating, we would see on the order of 1.25 inches at the top of the building. And that's an enormous pressure, especially given that there's a door up there and that the force on that door would be very, very strong. Virtually impossible for an individual to close by themselves. The way we were closing it was with basically a glass grabber, a suction cup on the top part of the door and someone operating the handle. It actually took 2 people to close the door. What we ended up sort of doing is sort of looking at a couple of issues here. And one issue was the lobby pressure distribution. What was happening was that the facade was carrying very little pressure and the elevators were taking it all. And that was because the facade either had a hole in it or the HVAC system was pressurizing the lobby. And when we sort of looked in it, it turns out it was the HVAC system. And the mitigation in this particular case was to try and rebalance the pressurization in the lobby and sort of change the behavior so people weren't sort of turning that one up because they thought it would make it better at the front door. It was just moving the problem to the elevators. The next one about the toilet exhaust being positive to some units, the transfer of odor from a unit to unit is clearly a problem. And what was ending up happening here was the toilets were set up where 50% diversity. That's okay, I'm not critiquing that. But the flows into each unit were based on a floor area of the toilet, and the fans were struggling to keep up. And we sort of did some modeling. And what you're looking at here is for different levels in the building, for different flow rates in the toilet riser, looking at what happens when you open a window on a couple of floors. And so what this is set up to be is the flow going into the toilet exhaust based upon different toilet fan operation. And really the most important thing for you to note is that I've got negative flow here. This is outflow from the toilet, mostly from toilets exhausts that are closed. And so what's happening here is this toilet exhaust is running, this one's closed, this one's running, that one's closed. So anywhere you see a bump up is because the toilet fan is operating. And the reason why these two are so high is because the window is open. And so we could actually create conditions that would lead to flow coming out the toilet risers. And so the control of the toilet exhaust fans is crucial. In this particular case, the exhaust fans are on VFD, so that's fine. But there's a sensor located in a duct near the fan and another on an arbitrary hallway. In this particular case, we really need to move the sensors to places where we know absolutely that they're going to be reporting what we need. We need a sensor at the far end of the toilet riser so that we know that that is negative with respect to the hallway. So it's about making sure you've got your control set up is really important. And then the last issue was the unit door pressures. We were measuring pressures on the unit doors that exceeded what we would call a safety level. And when a unit resident opens a window, then the facade doesn't hold the pressure anymore. And so the pressure that's normally held by the facade moves to the unit door. We measured 165 pascals, so that's on the order of 0.6, 0.7 of an inch on an upper unit door that was 24 square feet in size. So that force to actually try and close that door was enormous. That's on a unit door. So think about a small child, a smaller individual trying to move that door or trying to prevent it from whacking into them when they open it. That can be a problem. So we got to be careful with high pressurization rates at the top and bottom of the building to make sure that those don't exacerbate any issues. And then the final issue I'm going to talk about is at the top of the building at level 78, there's a lift machine room. So the elevator machine room is here. Of course, that means that there's holes to the shafts below in this building. So this room is directly connected to the bottom of the building. And that we found that this space here, which should have been interior space, had doors to the stairs and a door to a semi-outdoor space. But this space was behaving like it's external. And it meant that the force on this door was 3/4 of an inch of water, which made that very, very difficult to close. And in this particular case, this is about diagnosing and trying to figure out why what should be interior space is actually exterior. And it just turns out some poor choice of fan components, some unawareness of how fans were operating and opening dampers led to this being an outdoor space. In this particular case, the stairwell was carrying a similar pressure. And so that stairwell actually became very, very difficult to open and close as well. So I'm going to stop here. I think if I'm going to close this up, there's sort of three things I needed to sort of highlight for you. One is that stack effect's going to exist in a building that has a different temperature for outside no matter what. And there's things that you can do to mitigate it. I promised to let you know how to eliminate stack effect. And the way you eliminate stack effect is basically to get rid of the temperature difference inside and outside. But that's not the entire building, it's actually the shaft. If you can make the shafts in a building have the same or similar temperature to outside, you significantly reduce the stack effect driving force. I don't care what the temperature is on any particular floor. What I care about from stack effect perspective is what the temperature is in the shaft. So if I can manage the temperature in the shaft, then I can start to manage the overall stack effect driving force. clearly, if you're going to go and try and manage the stack effect forces by changing the temperature in the shaft, that's going to change the design of that shaft. And so all of a sudden we're into insulation on the shaft wall. You might have to heat or cool the elevator cab. You can't put piping in there because it may drop, it may get cool. So there's a whole bunch of things that have to be taken care of, but it is possible to eliminate stack effect in the building, but it's got to be done from the beginning. And so with that, I will end this webinar and happy to sort of sit and answer questions. And as I said, I'm happy to stay beyond 6 o'clock.
All right, thank you,
How do we
Duncan.
do on questions?
We have a couple questions. So just a reminder to everybody, if you do have questions, please put them in the questions box. So the first question is, do you use multi-zone network airflow models to study the more complex problems?
Yep. So big shout out to NIST at this point, and I know the fellow who did a lot of the coding for CONTEM. We use CONTEM for multi-zone network flow modeling, and the examples I was showing were all done analysis, all driven by CONTEM. We have our own front end, just simply because we find the CONTEM front end a little awkward to create complex buildings in, but you can do it. And I know that there exists, I think you can buy or rent or license front ends for CONTEM as well. But the engine, the solver engine in CONTEM is awesome. It really is fabulous. There are some people who use CFD to try and do stack effect studies. That can work. It's probably a lot more effort than is necessary to set up a CFD model to study stack effect, where something like CONTEM can happily do that for you a lot quicker.
These two questions are related from two different participants. One would like to know, how do you measure the pressure difference across the facade of the, sorry, let me start again. How do you measure the pressure difference across these facade in an existing building without disturbing the facade? And another participant would like to know, what instruments do you use to measure the pressures? Okay.
So I'm going to draw for a minute. So yeah, the question about Schrodinger's cat and measuring something and you change it. When I was doing this plot and saying that the total delta P is some number, and I was sort of let's say 14 PSF, and I sort of said that this represents the pressure from the outside all the way to the elevator core, and this represents the pressure all the way to the elevator core. What you need to do on, let's say, a residential unit is, and I'm going to get to that question in a moment, but I got to sort of answer some other thing first. If this is my elevator shaft, this is my corridor, and these are my residential units, and let's say this is a nice building and I have 4 residential units, there's a door on the residential unit. I have to measure the pressure from the elevator core to the outside through every single element that might block the pressure. So I got to measure across the elevator door, across the unit door, and across the facade. Usually between the elevator door, measuring between the elevator doors isn't a problem. You just jam your manometer tube in past the doors. The doors might object a little bit, but you can usually do it. Same thing with the door here. You can usually jam something underneath the door and close the door tight, such that you've still got enough of a gap for your tube. The facade is the most difficult one. I'll sort of save the best to last. Usually what we do is find a door that's got a small opening in it anyway, or stick the tube underneath and pull the door closed. And if you close the door tight, as long as there's enough of a gap in that tube for air to sort of slowly pull out or slowly push in to equalize the pressures in the tube, you'll get a decent pressure measurement. If you crimp the tube completely, you will not get a decent pressure measurement. So the other way to do it is to then sort of take an absolute pressure here and then take an absolute pressure out there and subtract the two. That will give it to you. So an absolute pressure can come from a variety of tools, but there are barometers that will allow you to take an absolute pressure. The challenge with using a barometer is usually they're not as precise as a manometer that's taking a delta P. So when I was presenting plots like this that we had taken in a building, they always take at least a minimum of 2 pressures, and that's usually the facade pressure and the elevator door pressure. And if there's a unit door in the way or something else, then it would include that as well. So I think that was 2 questions, right? How do you take it across the facade? And then the other one is what's the instrumentation? So so there's 2 pieces of instrumentation I had flagged. One is a delta P manometer. And there's a variety. Literally, if you go on Amazon, you can find them. And you're looking for a manometer that's taking delta P's, and your kind of range that you're after is sort of plus or minus 2 inches. That's the kind of range you're going to need. The other option is to have an absolute barometer. Anything that you have on you that measures altitude. So some people's watch measure altitude by pressure. Some people have so like a temperature gauge that might measure altitude. Those are actually reading a barometric pressure. So you can actually use one of those and convert it. You just need to make sure you understand where the reference is. But if you stand inside a building and you take an altitude measurement, and then you walk outside the building and close the door and take an altitude measurement, the change in altitude is actually purely associated with the delta P that you measure. So that you could use that as well.
Okay. Next question is, what is your experience using constant air regulators, CARs, for balancing air outlets, toilet exhaust, kitchen exhaust, outdoor air for high-rise residential?
Yeah.
Sorry, there's one more piece. Is please also reiterate HVAC balancing measures to mitigate stack effect.
Okay. Another clean page here. So, so constant air volume regulators make an awful lot of sense. And bear with me while I sort of draw that up for a moment. If you have a building, and let's sort of put an elevator shaft in the building. Give me, it's not a straight line, and then we know in this building that this is the delta P. I've sort of consciously sort of just put the neutral plane a little bit lower than halfway. If you're trying to push air into this building through the HVAC system, you're going to be working against stack effect forces. Now, what often happens so now let's talk about different locations. For those of you who work only in New York seems to have a method of designing residential units that is different from Toronto and is different from Chicago. So for example, in Toronto, what will end up happening is that these residential units will all have through the wall energy recovery ventilators. And these ERVs will penetrate the facade and then have a silly little fan in there and a backdraft damper. This is in Toronto. In Chicago, what will end up happening is that there'll be an operable window on this building. There'll be makeup air into the corridor, and then there'll be a toilet exhaust that's centralized. And so this toilet exhaust that's centralized is pulling air out. And so now you can imagine that if I've got one riser for toilet exhaust that runs the height of this building, and this building doesn't have to be tall, and I open a window here, and I open a window up here, this open window at the bottom of the building may actually pressurize the toilet exhaust shaft or toilet exhaust riser so much that the fan isn't able to keep up. So what ends up happening is I get toilet exhaust leaving up here. What a constant volume regulator will do is stop this open window at the bottom from overpressurizing that riser. So they can be very useful. If you know they're going to be reliable and they can take the pressure, they can make it so that your toilet exhaust and your makeup air isn't being overdriven or underdriven. This then helps you with balancing once you start getting into it. Sometimes what we find in some buildings is that there's 1 or 2 fans that are dealing with multiple risers that are dealing with different stacks of units in a building. And so if I sort of look at a floor plate, let's sort of say I have a floor plate here and I have a bunch of units that are on this floor, and what happens is all of them have at least one toilet. I might have a stack of toilet exhaust here and a stack of toilet exhaust here. and so on and so forth as I go up the building. But what ends up happening is on one floor, they're all connected somewhere. And the way in which these are connected actually starts to become a bit of an issue, because we might find that, that's my exhaust, that this particular branch may end up taking the risers from multiple parts of the building. And so when you start coming to balance this, it gets very, very difficult. And then when you throw stack effect pressures on it, all of a sudden it can't keep up. So what you're better off doing is making sure that the connections from all the risers to the fan, if you're going to use multiple risers on one fan, that they're all the same, that the paths are all the same, so you can do a better job of controlling the pressures in the risers at the fan rather than controlling branches as you come off. So, you know, there's sort of two things there. One is those constant volume, constant flow dampers are really useful. And then the second thing is you can make your life for balancing a lot easier if you keep the branches the same and minimize the sort of connections as something goes, or as a duct goes out to the riser. I hope that answers that question. There's a lot of stuff in that to answer that question completely.
Okay, yes. So we do have one person that would like to stay after, that would like to have a conversation. So we'll do that. But for everybody else, that is all the questions that we have for right now. So if you would like to stay on and hear the remaining of the conversation, feel free. If not, please sign off, and don't forget to fill out the survey. That's how we're tracking attendance. And from that survey, we'll be able to know, be able to provide you with your PDH certificate via email, as well as a survey of the webinar. So we thank everybody, and we will see you next time.